Okay, Chemistry 2342. Here is the second part of Chapter 19, Part 2. We're going to talk about additional condensation reactions. So let's first talk about the differences between the aldol and the Claisen, okay? In the aldol, we use aldehydes or ketones as the substrate. In the Claisens, we always use an ester as a substrate, okay? Mechanistically, it's in the last step where the alkoxide in the aldol is protonated, but in the Claisen, what happens is the electrons kick in and kick out an alcohol, giving us a carbonyl compound. So if you can think about it, the aldol will give us the keto hydroxy compound, and the Claisen will give us the keto compound. Okay, and it all has to do with the idea that what the leaving group is. In the Claisen, we have an alkoxide as our leaving group, which is a fairly decent leaving group, and it lets us generate that carbonyl compound. However, if we try to do that same thing with the aldehyde or ketone products, what we're ending up doing is we're trying to remove a hydride ion or a carbanion, and so those are very poor leaving groups. So those are less likely to leave. Therefore, we will keep this alcohol until we do something else to it, like either until we do something else like a dehydration reaction. Okay. So we can actually do a mixed condensation of an aldol, and that's where we have two different compounds used in the aldol addition. Unfortunately, if you just mix two different aldehydes together, you're going to end up with four products. Aldehyde 1 will react with aldehyde 1, aldehyde 2 will react with aldehyde 2, aldehyde 1 will react as the nucleophile, aldehyde 2 will react as the nucleophile. So you'll end up with a total of four different systems, and there's a very good description of this in the book if you want to get additional information. Now, there is an exception to this rule. If one of the carbonyl compounds has no alpha hydrogens, that means you only get two products possible. Okay, and the reason is you form the enolate, and that enolate can only react with the other compound. And if you have the compound with no alpha hydrogens in excess, that means it's going to react with that one first because there's more of it available, and you're likely to get a single product as your major product. So for example, in this case here, we have this benzaldehyde here, and notice it has no alpha hydrogens here. Now, if we slowly add our aldehyde here with alpha hydrogens here in the presence of a base right here, it'll slowly deprotonate that, and then because we're adding this slowly, we're only making a little bit of that enolate at a time. As soon as that enolate forms, it reacts with the other aldehyde with no alpha hydrogens, giving us our major product here. And then what an additional further product that happens is we can actually get dehydration to form a conjugated alkene. Okay, so the second thing we can do here in this mixed aldol addition is that we can use, instead of a reversible base like an alkoxide or hydroxide, we actually use an irreversible, kinetically driven base like LDA. We learned last time that LDA gives us our kinetic one. It takes off the hydrogen where it has the most hydrogens, generates that enolate, and makes it irreversible. Once we form that, we can then slowly add our other compound here. Our enolate will react with that carbonyl compound to give us our alpha hydroxy ketone compound, okay? So if we look at this one right here, this example here, we have LDA, it deprotonates at either one of these alpha hydrogens here, giving us our irreversible enolate. And if we start slowly adding this in, our enolate will attack at this carbonyl. And because we can't eliminate a carbanion or a hydride, we end up keeping the alcohol in this system here. Okay, so now remember that LDA will always give us the kinetic one, the one with more hydrogens on it, as opposed to the thermodynamic system. So we'll always look for that happening and it works especially well in these ketones. Okay, so we can also do this in a mixture of esters with aldehydes and ketones, but it works best if you can form your system with an aldehyde or an ester, with a mixed an aldehyde ketone with an ester. And the reason is that the ketone has more acidic hydrogens than the ester has. Remember, the oxygen on the carbonyl here decreases the acidity of these protons. And therefore, if that's true, that means we're going to form this enolate as our primary enolate to be formed because they're more acidic. And then it will come in here, attack the carbonyl. And then, of course, just like in the Claisen condensation reactions, we actually kick out ethanol, and it gives us our beta diketone compound. Now, if you want to form an aldehyde with the system, you just have to design it correctly. You want to, again, use your ketone right here. And remember, it's going to form that ketone is the only way you're going to form the enolate ion here. It is then going to attack your aldehyde. And again, it's going to not kick out a hydride. It's going to kick out the ethoxide as your leaving group. Therefore, you're going to get your ketone from your keto species you started with, but the aldehyde comes from the fact that you're using the ester of formic acid. And that's how you can get this beta ketoaldehyde compound here by adding just that extra carbon. Okay, just as we did with the Diekmann addition reaction, we can also do an intramolecular aldol condensation, okay? Now, the key with doing an intramolecular alcohol condensation is you're always going to form a 5 or 6-membered ring. So even if you end up doing what you think, well, you know, the inside hydrogens would be more thermodynamically stable, even if they did form them, what would happen is, in this case here, if we had this the 1,4-diketo compound here, even if we did form the more thermodynamically stable enolate right here, when it tried to close that ring, it would make a 3-membered ring. A 3-membered ring is very highly strained and therefore does not form. So instead, what we'll have is we'll actually get the kinetically removed proton here. The kinetically removed proton can then create this 5-membered transition state, allowing us to close that ring and keep that ring closed. And then when we acidoize, we generate our beta hydroxyketone compound. Notice we can do that with additional systems. If we extend that ring out a little bit more, we can actually use this longer 1,6-diketone, and instead of taking away this this kinetic proton, we can actually make that 5-membered ring by removing the thermodynamic proton here. So in this case here, it's not about whether you're forming the kinetic or the thermodynamic product, it's forming the stable intermediate, either that 5 or 6-membered ring. So in this case right here, with the kinetic product, you're going to end up with a 7-membered ring, and due to entropy, that 7-membered ring is not typically formed, so we don't see that as a major product. Okay, but here we're actually taking the thermodynamic enolate formation. Now it can form that 5-member transition state, and in forming that 5-member transition state, it creates a nice stable product, and then it can give us our beta hydroxyketone product. Okay, so let's continue on with the aldol condensation and what can happen immediately after it reacts. So when we create that aldol condensation, we end up first with our beta hydroxyaldehyde here, but we have an acid or base catalyzed dehydration of an alcohol to create an alkene. And in the aldol condensation here, it's really favored because you end up with a conjugated double bond here. The carbonyl counts as a double bond, and then the new alkene counts as a double bond. So we end up with this alpha-beta unsaturated aldehyde. Now remember, this dehydration does work with acid or base, so we can either do it stepwise, stopping at this hydroxide and then adding acid and heat, or we can just, after the reaction is done, just heat it up and liberate water in both cases. This will give us those alpha-beta unsaturated ketones or alpha-beta unsaturated aldehydes. Now, the cool thing about these alpha-beta unsaturated ketones or aldehydes is they can react in a 1,4 addition or a 1,2 addition just the way dienes will. Okay, And when we do that, we call them conjugate addition reactions, okay? So if we think about it here, we have our unsaturated uh, compound here. It looks like a diene. We have a partially positive carbon here, a partially positive carbon here, and a partially negative oxygen here. Okay. When a nucleophile comes in, it has a couple different choices. It can either attack the carbonyl right here, giving us a simple addition reaction, and that creates an alcohol that is one carbon over from an alkene, or we can get the addition of the nucleophile to the other partially positive carbon here, giving us our enol form, which of course would rearrange to give us our keto form by moving this hydrogen over in this direction here. And so technically this counts as a conjugate addition because this is our 1, 2, 3, 4 position. So this simple addition is our 1, 2 addition, and this is our 1, 4 addition. So just like we see that with dienes, a 1, 2, and 1, 4, we get that same kind of addition in these alpha, beta, unsaturated aldehydes and ketones. Okay. Now, what drives the reaction here? The stronger the nucleophile, the harder the anion, the more a simple addition is favored, the more it is going to add to the carbonyl compound. If you have weaker nucleophiles like enolates or cyanide ions, or you're looking at the lone pairs on amines or the lone pairs on alcohols, those are likely to give us the 1,4 conjugate addition reactions, okay? Now, also, the less sterically hindered the CO is, the more likely it is to undergo that addition, meaning that aldehydes will give the direct addition products more often than ketones will. Okay, so let's look at that as a function of the strength of the nucleophile. Again, like I said before, if we have a strong anion, like in the case of a Grignard reaction, the major product is going to be our simple addition, our 1, 2 addition here, with a bit of our minor product being the conjugate addition here. So if we think about it, that is a very strong anion. In the case of sodium borohydride, we have hydride is our actual nucleophile in the system, and therefore it also gives the direct 1, 2 addition product by giving us the alcohol here, okay? So we see that happen in really, really strong nucleophiles like carbanions and hydride ions. Okay. And this is another example here at the bottom where we've done it with, again, sodium borohydride with this addition product here. We get about a 50-50 mixture of the simple addition versus the other addition, but then it can further reduce down to give us a little bit of this unconjugated reduced secondary alcohol. Okay, so if Grignard reactions give us 1, 2 additions, do we have other nucleophiles that'll give us that 1, 4 predominantly? And we do. In our Grignard reaction chapter, we also had these copper based nucleophiles, okay? In the copper-based nucleophile, where we have the alkyl copper lithium compound, that's a less polar bond, and if it's a less polar bond, that makes it a weaker nucleophile. Therefore, instead of getting just the simple 1, 2 addition that we would get from a Grignard reaction, we actually get more of the 1, 4 addition from the conjugate addition reaction that we don't get in the Grignard. So one way to add that carbon-carbon bond is to go with the less nucleophilic Gilman reagent, and instead of a Grignard reagent, and we will get to our 1, 4 addition product versus our 1, 2 addition products. What else can we do with these nucleophiles here? Again, the weaker the nucleophile, the more likely we are to form the 1, 4 addition product. So in this simple one where we have this alpha beta unsaturated ketone here, we can actually have the cyanide come in at the 4 position, kicking out our carbonyl, giving us our carbonyl here. So it's going to go in the hydrogen is going to, it'll give us our enol form right here, which will then rearrange to our keto form after addition of acid. Here, because the thiol is a weak nucleophile because it's not the anion, it is the simple thiol. It acts as a weak nucleophile and also gives us this addition here, which will kick out, giving us our um, enol form, which will then rearrange to our keto form after quenching the reaction. And we can get the same thing happen with our nitrogen-based compounds. Again, the lone pair on the nitrogen here is the one that's doing the addition here, kicking this out. And then once we rearrange with our enol keto, we end up with our 1,4 addition product. Okay, so weak nucleophiles give us more 1,4 products. Strong nucleophiles like Grignard reagents and hydrides give us 1,2 addition products. And that's addition across the carbonyl.